SwayamPrabha. Digital India. Educated India.
Good afternoon, everybody. Today's lecture will start. If you recall, in the last class, we mentioned about our lesson plan. At the outset, we will learn the basic methodology related to finite difference, finite volume, and finite element techniques. We will apply these techniques to simplified transport equations and try to understand different characters of the problems and formulation strategies. Having done that, we will switch over to full-fledged solvers. So today we will start with finite difference methods. In our plan, we have the following. We will mention about discretization techniques to convert each term of the differential equation into finite difference quotients, and then those quotients are assembled to describe finite difference equations into the algebraic equations. Then we'll discuss about consistency. Then we'll take up some formulation strategies, whether to formulate the problems in an explicit method, or to follow implicit method, or to follow ADI method. This is alternate direction implicit method. While going through it, we'll learn a lot more about it. I'm just mentioning it now. Then we'll go for error analysis, which will culminate into stability analysis. Then we'll mention about conservative and transportive properties of the equations when the differential equations are converted into difference equations. How do they preserve conservative property and transportive property? What can be a better strategy to preserve all these properties? Then we'll mention about upwind differencing and higher order upwinding. And this, we'll do with the finite volume and finite element also, following finite difference strategies. And as I said, then we'll apply, all this knowledge for developing full-fledged solvers. So, discretization procedure is a procedure by which a continuous domain is divided into a discrete number of points. Basic idea is to replace differential equations by finite difference quotients. This results in a system of algebraic equations for replacing the differential equations. Now, if we have a look at a general second order equation given here, as you can see, a del 2 phi del x2 plus b del 2 phi del x del y plus c del 2 phi del y2 plus d del phi del x plus E del phi del y plus f into phi equal to g. If the coefficients a, b, c, d, e and f are either constants or functions of only x and y, that means they do not contain phi or its derivatives, it is said to be a linear equation. Otherwise, it is a nonlinear equation. An important subclass of nonlinear equations is quasi-linear equations. In this case, coefficients may contain phi or its first derivative, but not the second derivatives. If g equal to 0, the aforesaid equation is homogeneous. Otherwise, it is non-homogeneous. Now, from this A, B, C, D, E and F, we can determine the character of the equation. If b square minus 4ac is less than 0, then the equation is elliptic. If b square minus 4ac equal to 0, equation is parabolic. If b square minus 4ac is greater than 0, then the equation is hyperbolic. Depending on these characters of the equations, we have to choose different solution strategies. The unsteady Navier-Stokes equations, as you know, these are basically three equations in x, y and z directions. These are elliptic in space and parabolic in time. At steady state, the Navier-Stokes equations are elliptic. The Laplace equation and Poisson equation are generally associated with steady state problem. I have given here example of Laplace equation and Poisson equation. Now, it is very clear that space variables are involved in it, and these are steady state problems. And also character wise, these are elliptic equations. Next, you can see wave equation. Wave equation is hyperbolic equation. We'll discuss a lot more about it in course of our discussions. And then I have given very simple heat conduction equation. It is, basically phi will be substituted by temperature T if it becomes heat conduction equation, and B will be substituted by conductivity of the material. It means conductivity of the material. So this is basically one-dimensional heat conduction equation, which is parabolic in nature. Now, for unsteady two-dimensional problems, which can be described by the equation given here, either a flow problem or a heat transfer problem, then it will be energy equation. You can see del phi del t plus u del phi del x v del phi del y equal to d, then the double derivatives and plus s, where phi is the velocity of the field. In this direction, it is two-dimensional equation. So basically phi will be either u or v, or it will be temperature if it is energy equation. D is the diffusivity and S is a source term. If sources are present, as a special case. The formulation of a problem requires complete specification of the boundary and initial conditions in addition to the complete equation. Boundary conditions can be Dirichlet, Neumann and mixed. Dirichlet means the value of the dependent variable is directly defined, as you can see in this example, that phi equal to phi 1 and it is defined on A1. Then Neumann, it is basically the derivative in the normal direction. As you can see, it is defined on A2. And then also it is possible to have a condition where Dirichlet and Neumann condition are clubbed together. It's called mixed condition, and here it is on A3. So Neumann is on A2. I showed this side. Neumann is on A2. A2 is drawn on this side. Dirichlet is on A1 and mixed is on A3. So this is how the boundary conditions are defined. Now let us imagine a very simple network with horizontal and vertical lines that provide coordinates for locating points in a domain. This is the most important point, that the points in a domain should be defined through their coordinates. And in order to know that coordinate, you may have to draw some such vertical and horizontal lines in Cartesian coordinate system. In cylindrical polar, again this will be constant theta and constant r lines. Similarly, in spherical polar system also will have the respective grid system. Now delta x and delta y are the grid spacing, which can be uniform or non-uniform both. Here we have taken the uniform grid. As you can see, this is the location of ij point. If we move delta x towards east, coordinate of this point will be I plus 1j. If we move delta x towards west, then coordinate of this point will be I minus 1j. If we move delta y in the north, then coordinate of this point will be ij plus 1. If we move delta y in south, then the coordinate of this point will be ij minus 1. So finite difference representations of the derivatives obtained on all these points using Taylor series expansion. Very simple. Again, if we say u is a variable, dependent variable distributed over this domain, and value of u at ij point is known, then value of u at ij plus 1 point can be known by using Taylor series expansion. So ui plus 1j equal to uij plus del u del x at ij point into delta x plus del 2u del x2 multiplied by delta x square by 2. You know, all of us know that this is Taylor series expansion. But from here, it is possible to find out value of del u del x. As you can see, del u del x at ij point is u I plus 1j minus uij divided by delta x plus all other terms. If we shift to the other side, because we are trying to find out del u del x. So if everything is shifted to the other side, then after having this expression, the remaining terms are basically neglected. But we can say, if you look at the remaining terms, it will contain, because this term will be having highest contribution after going to the other side, it will contain higher order derivative and terms of some order. So here it is called first order because it is order of delta x. This delta x will divide all the terms on the other side. So this term will become del 2u del x2 into del x by 2. So, and this will be the highest contribution from the terms that we will be neglecting in the Taylor series. So this is called forward difference because the point of interest is in the forward direction, and the truncated series is having order of delta x. So this is called first order forward difference. Similarly, we can have other elementary finite differences if we take backward or rearward difference. That means a point ui minus 1j which is in the westward direction from the point ij. So then it will be uij again del u del x at ij multiplied by minus delta x, del 2u del x2 at ij multiplied by minus delta x square by 2, del 3u del x3 at ij into minus del x cube by x, and so on. So from here we can approximate del u del x from ui minus 1 and uij. If we do that, since we have moved in the westward direction to get the Taylor series, it is called backward difference. And you can, just like the forward difference, here also order of accuracy, you can say it's first order accurate. However, now if you take equation 1 and 2 and you subtract 2 from 1 and then try to find out del u del x. So obviously you will get this term. So uij from 1 and 2 will cancel out. You will get on the right hand side twice del u del x into delta x, and then if you want to find out the quotient del u del x at point ij, you will be able to write ui plus 1j minus ui minus 1j divided by twice delta x. And again, after subtracting 2 from 1, the equation you get from there, if you find out the expression for del u del x as ui plus 1j minus ui minus 1j by twice delta x, you will have remaining terms which you can neglect. These remaining terms are having higher order derivatives and higher order terms, and since you are neglecting them and the highest order of the neglected series is of order delta x squared, so it's called second order central difference, and its accuracy is, as you can see, its accuracy is second order. So this is basically second order central difference of first order derivatives. Now if you add up 1 and 2, you will see that you will get as a result on left hand side ui plus 1j plus ui minus 1j, and on the right hand side you added up, you will get twice uij. All odd terms will get cancelled out and even terms will be there. So from there you can all even terms will get cancelled out and all odd terms will be there, and then you will be able to write an expression. So this will be the expression, and from here you can easily write down del 2u del x2 as u I plus 1j minus twice uij plus ui minus 1j divided by delta x square, and all remaining term will be dropped. So this quotient can be called as central difference of the second derivative. So this way, whether first derivative or second derivative or third derivative, whatever is the term in the difference equation, finite difference equation, so differential equation, you can get finite difference equivalent of that equation through these quotients. Now, combination of such finite difference quotients for partial derivatives form finite difference expressions for the partial differential equations. For example, if we consider Laplace equation, that means grad square u equal to 0. So double derivative of u in x direction plus double derivative of u in y direction equal to 0. And then del 2u del x2 we have substituted by this quotient. Del 2u del y2 we have substituted by this quotient. Now we can perform simple algebra from here. We can write down ui plus 1j plus ui minus 1j plus lambda square, where lambda is the aspect ratio of the grids. If delta x and delta y are same, then lambda is 1. But if they are different, then lambda will be having some value depending on the ratio of delta x and delta y. Then lambda square multiplied by ui j minus 1 plus ui j plus 1 plus ui j minus 1 minus twice 1 plus lambda square into uij equal to 0. Now from here we can again simplify and get an expression for uij. If you go back the figure 1, where ij template is there, ij, I plus 1j, I minus 1j, ij plus 1, ij minus 1, etc. There you can see that uij is now expressed in terms of neighboring nodes and then divided by 2, 1 plus lambda square. If lambda is 1, then it will be 4. And it will be simple average of all the neighboring values of neighboring nodes. So that means if you have some initial distribution of u known in the domain, and then maybe the domain is subjected to some change. Maybe you have started heating from one end, you have started cooling from one end, and you want to find out, and domain is a maybe conducting material, want to find out final temperature of that domain. So that will be equivalent to uij at each point. So at each point it will be the basically function of 4 neighboring nodes, some divided by 2 plus 1 plus 2 into 1 plus lambda square. And this way, if you can vary I location from maybe I equal to 1 to maximum number of points you have in the domain, j equal to 1 from maximum number of points you have in the domain, maybe 1 to 100, I j 1 to 100, then every uij you will be able to calculate in terms of its 4 neighbors. And if the values are changing, you will be able to update uij. And this way, iteratively, if you keep on calculating, at one point of time, you will see that these values of uij's are not changing anymore. It has reached a steady state. That will be the solution of this grad square u equal to 0. This equation, if u is, the example I gave, there u is mean temperature. So you will get the temperature, final temperature distribution on that domain. So it can be said that many other forms of difference approximations can be obtained for the derivatives which constitute the governing equations for fluid flow and heat transfer. The basic procedure, however, remains the same. So here I will give an example of a mixed derivative. The same approach can be made to generate the finite difference quotient for the mixed derivative, say del 2u del x del y at grid point ij. So we can write del 2u del x del y as del del x of del u del y. In the above equation, if we write x derivative as a central difference of y derivatives and further make use of central difference of x derivatives, then we will be able to obtain the expression. So here del, you can see we have written del del x of del u del y. That means we want to find out it at a point ij. So we have taken del u del y at one point east, that means I plus 1j, and at one point westwards del u del y at I minus 1j divided by twice delta x, retaining second order accuracy. Now these terms we will expand in the next step. So these will be expressed as the I plus 1, this point has been fixed. At this point we will find out y derivative. So we will go j plus 1, that means 1 point in the northward direction, j minus 1, 1 point in the southward direction, and divide by twice delta y. Same we will do at I minus 1 j point. We will find out quotient of del u del y by writing down difference between the northern point, southern point divided by the distance between the northern point and southern point. So we can summarize this as del 2u del x del y equal to 1 by 4 delta x into delta y. Within bracket we have u I plus 1 j plus 1, u j minus 1 I minus 1 j minus 1, u I plus 1 j minus 1 minus u I minus 1 j plus 1. All neighboring points at the point of interest, that means ij, will be able to find out the quotient this way. And you can see this is second order accurate. Second order accurate in x direction, second order accurate in y direction. So now let us look at the truncation errors. So when we found out forward difference, we said that we'll find out quotient and neglect the remaining terms of the series. So if we neglect the remaining terms of the series, in the first order forward difference, you try to recall, we wrote u I plus 1j minus ui minus 1j by ui plus 1j minus uij by delta x. And there, this was the truncation series, and highest order term in the truncated series is this, because next terms are even higher, delta x, square, delta x cube. So obviously these will be having less and less contributions. So this will be having highest contribution. Similarly, first order backward difference will get the truncated series, and if we write the truncated series, this term will have the highest contribution. So this is the case of with first order backward difference. And in the case of central difference, if we look at the truncated series, then highest contribution is made by this term, which contains third order derivative and second order term, second order delta x square. So these are the expressions for truncated series and the highest contribution in the truncated series. And since these are being neglected, so they contribute in errors, and we will call them truncation errors. So a finite difference representation of a partial differential equation will be consistent if we set a limit that partial differential equation minus finite difference equation, finite difference equivalent, as mesh tends to 0, that means truncation error, as mesh tends to 0, what it will be. Now, this truncation error as mesh tends to 0, if it becomes 0, then it is basically consistent. The solution of partial differential equation, in addition to consistency, this is another condition. The solution of finite difference equation is convergent if the approximate solution that is obtained approaches the exact solution of the partial difference differential equation at each point as the grid spacing tends to 0. These are almost equivalent statements. This is qualified little further to give the convergence, and this is called consistency, or consistency, or formulation is consistent. Now, see, let us look at different formulation strategies. One-dimensional unsteady state heat conduction equation. Again, we can write del U del T equal to alpha del 2U del x2. We have written it in a generic way. U usually used for flow variables, but we can here use it as temperature. Then alpha will be the basically thermal diffusivity, or thermal, in this case, basically thermal conductivity. So using FTCS method, the discretization, that means del U del T will have U n plus 1. You must have noticed that we are using n for the time direction, for the time domain, and ij for the spatial direction, for the spatial domain. So del U del T, U n plus 1 in the time direction, from the present time level in the forward direction, n plus 1 minus uyn at ith point by delta t, and then this is plain second order derivative in space, u I plus 1 at nth level minus ui at nth level plus ui minus 1 at nth level delta x squared. So in x direction, 1 point eastward, 1 point westward, and the point of interest at nth level. That means to start with, if the values are known, then you will be able to easily find out what is this. And from there, you can do the time marching of the solution in n plus 1 direction, in the time direction. When delta t and delta x, these two approach 0, the truncation error also approaches 0. Such a partial differential representation is said to be consistent. That's what I mentioned earlier, that if truncation error becomes 0, then the formulation is consistent. Here we can collect the truncation errors, and we can see if we set delta t and delta x to 0, whether they are tending to 0 or they are becoming 0. If they become 0, then there is no problem. It is a consistent formulation. If they become non-zero, then there is a problem. It may not be a consistent formulation. So, can it really happen that we will discretize, assemble, and the equation, that means finite difference equivalent of the partial differential equation, will be such that when the limits are tending towards 0, the truncation error is not diminishing or not becoming 0. Let us take up an example. Earlier example was FTCS scheme, that which is called forward time and central in space. So, and as we have mentioned, that we can readily feel that truncation error goes to 0. But let us look at another formulation strategy. Again, let us consider it conduction equation. Here again, U should be imagined as temperature, alpha is the thermal conductivity, and thermal diffusivity, and basically this equation we discretized using FTCS method. Here we are going for a very well-known scheme, although we have not introduced all these schemes to you. We will do it in course of time, maybe through some assignments and through discussions as well. Now, Dufort-Frankel scheme, this scheme is very much used for compressible flow problems, and it's a higher order scheme than FTCS. Formally, it is second order in time and second order in space. So, Dufort-Frankel differencing scheme, which has higher order accuracy than FTCS, we can write it, and this is ui n plus 1 minus ui n minus 1 by twice delta t. You can clearly see that in the time domain it is second order accurate, equal to alpha into ui plus 1n minus ui n plus 1 minus ui n minus 1 plus ui minus 1 n divided by delta x squared. Let us not get confused what has been done here. Usual, if we imagine these two, that terms, we put it in a bracket, take minus sign common, then this is un plus 1 plus un minus 1. So twice un has been substituted by this. Originally this was, central difference was supposed to have ui plus 1n minus twice uin plus ui minus 1n. Twice uin has been substituted by uin plus 1 and uin minus 1. That means twice uin equal to uin plus 1 and ui plus uin minus 1. And that substitute twice uin, then expression becomes this. And this is yet increasing the order of accuracy. So let us look into the truncation errors. So simply first look at the left hand side. uin plus 1, you expand it in Taylor series. As you can see, there is a mistake. This will be del u del t into delta t. Remaining terms are correct. Del 2u delta t square into del 2u del t2 into delta t square, del 2u del t cube into delta t cube. So this is correctly written. ui n minus 1, again Taylor series, del u del t at point in. Please read this as del u del t. So equation A. So it is again usual Taylor series, equation B. Now if we subtract B from A to formulate this left hand side quotient, we will be able to do that, but we will be truncating the terms of higher order derivatives and higher order terms of the Taylor series, and then the highest order term. So obviously you can see that here basically this term will cancel out, this term will be these terms will be cancelled out, this term will be cancelled out because we are doing a minus b, and so this term will be there, and this term, that means third order derivative term, will contribute to the truncation error. So this will create maximum contribution in the truncation error. So we have retained that term. You can see del 3u del t3 at point ni del t cube by 6. This is the truncation error for the left hand side temporal derivative. Then we have again written the spatial derivatives, ui plus 1 at nth level, ui minus 1 at nth level. In the spatial direction, again we have written the Taylor series expansion, and we have tried to find out, because here truncation error, if you consider this as twice uin, then first truncation error you will be able to evaluate if you subtract expression for ui plus 1 and expression of ui minus 1 from expression for ui plus 1. And that is how, we get this as a truncation error. Then we have expressed twice uin as uin plus 1 plus uin minus 1 here. Due to that, we have introduced some error, and that error basically easily can be found out by adding a and b, and then since this term is at the right hand side, will be divided by delta x square. So this will be the truncation error arising out of that. Now if we combine them, we can see that this is the representation of finite difference equivalent of the partial differential equation using Dufault-Frankel scheme. And the truncation error, we have already calculated individual truncation error of the finite difference quotients, and if we add them up, we will get this term. Now, we are lucky if when we shrink the grid size and when that means we make the grid refinement, and in the time domain also we refine the time step, and both approach zero in such a way that this entire truncation error approaches zero. Then we are lucky, life is simple. But it may so happen, because this delta t and delta x are different independent variables. So if we approach them in such a way that delta x approaches zero faster than delta t, then we will see that instead of this term becoming zero, this will be a non-zero term. Since we are getting 0 by 0 form, so there is a possibility for some conditions that this entire truncation error will not converge to 0. Instead of, it will be something which is non-zero. And although we are unable to see it mathematically or computationally, because we have already written finite difference quotients and formed the finite difference equations of the partial differential equation, we have set the initial condition, we have given the boundary condition, we have solved it. But what we are solving, we do not know if the formulation is not consistent, because this truncation error is supposed to be zero. If this remains non-zero, the way delta x and delta y are changing, that makes a situation where this is non-zero. Then effectively we are solving this equation, because original equation was del u del t, and we had this term, but we have got this term here as truncation error. So if we add them up together, we will get some such expression. Our basic idea is that in order to have a consistent formulation, the truncation error will be zero and the finite difference equation will become partial differential equation exactly. Here it is not becoming that, leaving behind some non-zero terms. So, and if you try to characterize this equation, you will see this is hyperbolic equation. Reconstructed equation is hyperbolic. So original equation was parabolic. So this is not a consistent formulation. So therefore, it is understood that higher order schemes enhance formal order of accuracy. It is very well appreciated, and we will do that. We'll try to increase formal order of accuracy, but one has to be careful. The formulation should be done in such a way that it should be consistent. So one has to be careful about consistency and convergence. If it is not consistent, we'll have trouble in getting convergence in computer. And even if we get convergence, it will be a spurious solution. So, as I said, written here, one may end up with spurious solution. So, in conclusion, it can be said that finite difference formulation is apparently easy, you have the governing equations. You substitute term by term of the governing equations by finite difference quotients. You get the finite difference equations. You apply initial condition, apply boundary conditions, and then solve it. You get the solution after the convergence is achieved. In order to increase the accuracy, you go for higher order discretization. Of course, with simply one-dimensional heat conduction problem, it is very simple. You do not have many terms and you do not have many equations. But if it is full Navier-Stokes equations, or if it is basically even energy equation in 3 dimensions, then you will see you will have a truncated series, and in that truncated series, combined truncated series, all the individual quotients will contribute the error, and after combining them, when you are refining the grid, that means in principle you are trying to give a solution of the finite difference equation which is equivalent to the exact solution of the partial differential equation. You will see you are not consistent. Either problem is not converging, or even the problem converges, the result is spurious. So one has to keep in mind this aspect of finite difference formulation. I will stop here today. We will meet again in the next class.